Okay, cool. Then let's move on to kind of the fifth and the final exercise. So this exercise is called the Argon Network Builder exercise. So unlike the previous four exercises that are kind of like very broad purpose or more like general networks oriented, this is definitely kind of the narrowest or the most like niche of these exercises. So this was designed in kind of response to a particular pain point. And that is when we were teaching sort of classes that cover network methodology. The hardest point in kind of the semester that we would run into is when we would try to teach the statistical technique that's called exponential random graph models. And that's the statistical technique for modeling networks and sort of this process of how do networks form and what are kind of structural patterns in network. So the hardest thing we would run into is helping students like understand what ERGM is doing. How is ERGM different from just running, say, a logistic regression, and helping people build that kind of intuition about it. It's where the course kind of goes from like being more like surface level or like more easy to grasp concepts like network centrality into more statistical modeling. And that was a really hard transition point we noticed for a lot of our students. And that's what sort of motivated the development of this teaching exercise I'm going to describe. So the goal of this exercise is to help students sort of experiment with network simulation, build an intuition about like what the different terms and effects in exponential random graph models represent, and understand how estimation of different terms is sort of interdependent on the other terms being estimated. Yeah, so again, this might be like the narrowest of exercises we're going to present today, and that a lot of network courses aren't necessarily going to cover ERGMs or go into that detail. But we wanted to briefly describe this exercise for those who are interested in teaching about the topic of ERGMs. Yeah, so this is work also with Jasmine, Meng Xiao, and then Nashir. So we built this exercise where participants are going to use a web-based tool to be able to simulate networks according to exponential random graph models. And by simulating and doing this kind of interactive in-class teaching exercise, we hope we can help them develop intuitions about how exponential random graph models work in general. So this exercise is designed to be used sort of embedded within a course where you're already covering the topic of ERGMs. And after you've introduced the topic of ERGMs with slides and or readings, giving students a chance to like kind of experiment with it, play around, and develop more intuition about the technical methodological topic you've just covered. So that's kind of the context of where you would use this. So big picture, when you're teaching about ERGMs, the kind of idea is you have an observed network and you're doing statistical inference. So you're going from that observed network, you're estimating a model, and that model is going to have a set of parameters that we can kind of represent as a vector theta. So you're kind of normally the way you think about it is I take a network, I estimate the coefficients in a model, and those coefficients can correspond to different terms like the number of edges in the network, different star structures in the network, reciprocity, popularity, transitivity, different types of network patterns that represent interdependencies and how one sort of social connection in a network may be related to other social connections in a network. So how do we help learners sort of develop intuitions about what these terms represent or how to put them together into a model? So that's where we came up with the idea of looking at using the thetas, so the coefficients in the model, and using them to simulate new networks. So that's something that's already done in kind of the Monte Carlo maximum likelihood estimation process for ERGM. But we wanted to use sort of this process of like generating networks as a way to help students build intuition about like, what are the different terms in the model doing? So if I like change one of the coefficients and I kind of like dial it up dial it down, how is that going to change the type of network that it corresponds to? How do those networks look differently? And that was kind of the goal of building this exercise. So we want to have them to have intuition about what the terms in an ergon model are representing and about the interdependence between effects included in the model. So how if I like change one effect, then I may also need to change the other effects around that. How are the different effects kind of interacting to produce, based off of these local properties, the sort of complex structure in the network as a whole? So there's kind of two links I have here, or two parts to the exercise. So I'm going to show you the platform first, and then I'll show you the kind of worksheet and the exercises around the platform. So this is a web-based platform, meaning it's entirely in your browser. In this case, it was implemented via NetLogo Web. But it's kind of a simple interface for simulating networks. So I can click setup and it will generate a set of nodes in my network. So in this case, let's do 16 different nodes and I'm going to set it up. And if I click go, it's going to move through Markov chain Monte Carlo steps and it's just going to simulate a network. So there's nodes and it's drawn these connections between all the different nodes in the network. And in these plots on the right, we can see it's sort of visualizing different properties of the network as we run the simulation. So in this case, we have the density of the network. We have the number of reciprocated ties, the number of homophilous arcs. So that's the number of ties between nodes that are the same. In this case, the homophily is based off of node coloring. So green nodes and red nodes, and how many ties are between nodes of the same color. And then we have triad statistics like the number of transitive and the number of cyclic triads. So where's the simulation kind of coming from? And it's coming from these sets of parameters. So these are like the ergon terms you would put in. So like the edges coefficient. So if I make this value larger and I run it, it's going to increase the density of the network. So there's a lot more ties. So you can see that kind of jumped up. Whereas if I make the edges term negative, then we're going to get a sparser network as ties are less frequent. Let me turn that down a little bit just so that we can see network structure a little better. So we have the network properties and we're able to like manipulate these properties. So in this case, if I make the edges very low and I make the homophily very high, then this network isn't clustered well, but we would see that there's a lot more ties from green nodes to green nodes and more ties from red nodes to red nodes relative to red to green ties. And basically, this just provides an interface for you to play around with patterns. So like patterns like 2 stars, manipulate kind of the coefficients in the ergon model and seeing how changing those coefficients has consequences for what the network looks like. So that then takes us to our sort of activity. So this is something we run as an in-class exercise. Let me just quickly zoom in on this a little more. Yeah, so we run this as an in-class exercise, and we have this handout that we can either print it or we can put it, just share a link. So it describes the exercise in a bit more detail. It provides a link to the platform, and it provides on the second page, we just have instructions. This is what the interface looks like. This is how it works to run the simulations and what it's doing. And then we have a couple activities. So we typically have students work in like small groups of like 2 to 3 people. We ask them to kind of sit around one computer and then like all kind of work on that computer together. So in each of the activities, we give them sort of a set of values to fix. So in this case, use a certain number of nodes, fix the edges coefficient at -3, and a set of parameters to experiment with. So looking at, say, the number of red nodes and manipulating that either to be higher or lower and seeing if I change that, how does the network look differently? So if I change the composition of my network or nodes, I'm going to see a very different network look. I'm going to see a very different network even if the ergom coefficients are exactly the same, because the node composition and the node kind of demographic attributes have changed. And similarly, we can ask them to manipulate the ergom coefficient. So for homophily, trying a positive homophily effect, trying a negative homophily effect, and seeing how the simulated networks look different by manipulating the parameters. And what this process does is it gets students to reflect on what are the different terms doing in the model, and guiding them through that. So we'll have students work on this exercise for say 5 minutes, 10 minutes. And then after they're done kind of working on it and discussing their small groups, then we'll kind of circle back up, have a large group discussion, and be able to like sort of call on students, ask them to summarize what they found, what they experimented with, what questions they had. And that provides a really good teaching moment. So the first exercise is homophily. Activity 2, we have them look at n-degree preferential attachment. So like sort of a degree popularity or a kind of a rich get richer effect, where if I have one incoming tie, it's more likely other nodes are also going to have an incoming tie that goes to me as well. So we kind of ask them to experiment with different sets of parameters for that, and then reflecting on it. And then on the last page, we have a couple concluding takeaways, but that's something we can also just cover in sort of the large group discussion after the second exercise. Let me go back to the slides. So that's sort of the big picture of what the ergom builder exercise is. We built it to help just with students to build intuition about this one model of exponential random graph models. But by helping them build intuition about this, it's also kind of a good segue or like a starting point for other methods we tend to cover later in the course, such as autologistic actor attribute models or other models like Sienna that are doing more complicated simulations. Yeah, so that's a big picture of what the exercise looks like. Are there any questions on this exercise?
So for the desktop version of that logo, is it uploaded? Can I access it from the desktop version of the logo?
Yeah, so this is run actually in NetLogo Web, which is, so essentially the team behind NetLogo has built it. So NetLogo Web is able to run kind of model standalone. You can also like kind of program in NetLogo Web if you want to, but it has most of the functions and most of the features in the desktop NetLogo, though it may be slightly different. But kind of what that allows us to do for teaching is that the whole thing's kind of hosted on the web. So you can kind of run it. And if you actually click at the bottom, you can see like the full NetLogo code. In this case, that's maybe only really useful if you're teaching a class on like agent-based modeling that uses NetLogo. But the whole thing is sort of, it's not running on like an external server. We're not running it, but it's just kind of running in your browser. So NetLogo was just kind of a convenient way for us to build that, where it's just going to run off of your browser in kind of an HTML file that's built using NetLogo syntax. But also, if you wanted a desktop version, it's possible to like export it to just a NetLogo file that you can open with desktop NetLogo, or export it as an HTML file if you wanted to like upload it somewhere else, or like embed it into like a course site or like a course learning material.
Yeah, sure.
This is just really nice. Thank you for all the tools you guys gave today. It's just absolutely so helpful here. But I guess my question is on this is, if one had access to this, could you use a different data set? And, you know, put that in to teach something the students would be working in? Like, for example, if you wanted to use 2 or 3 of these tools, it'd be nice to have I have a team that works all term on a digital history class, for example. And it's kind of nice to see, you know, infiltrate a couple of these tools to do it. And for sure, we've used the worksheets, I'm sure other people do the same. We developed and what we did, but I find it very interesting. You know, because I use historical data sets. It's interesting. I don't know if it's true.
Yeah, no, that's a good question. Kind of the way it works right now is that you're not kind of, we don't have it set up to put an empirical data set in because sort of the all the ties and that type of thing is kind of generated from the model. So it's kind of the it's kind of the flip side of like what an ergom is, where normally with estimating an ergom, you take a known network and you get the parameters. And this exercise is letting students like manipulate the parameters and get a network. So if you wanted to like kind of build it around like a specific network where you have in class, or one thing you could do is you could just like kind of manipulate the number of nodes. And right now it only does one demographic attribute. That would be pretty, I think, easy to like add other demographic attributes for a distribution. And that's essentially kind of the part that's kind of the setup. And then all the ties and everything that happens after that is just going to come from the coefficients that you manipulate here. So one way that we haven't used it before, but that would be maybe an interesting use case, is if I have like a ergom that was fit and I like presented that in like my slides where it was fit off of a network of like 30 people. And I knew what all the coefficients were. I could like plug in those coefficients here, like taking like, oh, the edges term in the paper was 0.9. The reciprocity term in the paper was like 1 point or like 2.1. If I plug those in here, and then if I run this for long enough, I should get like a network that resembles the original network from the empirical data. So you could kind of like take existing fit ergoms and kind of plug them in here. And that'd be an interesting potential use. Did that answer the question?
That's good. Thank you so much. I even understood it. That's good.
Yeah, no, it's kind of a weird way of like thinking about statistical modeling, in that it's kind of forcing learners to go and look at I have to actually manipulate the parameters myself and set this like by hand. And by doing it by hand, I have to understand like what the parameters are doing to like set up the network that's being simulated. So you're kind of having the students like manually do what normally the Markov chain Monte Carlo estimation process does automatically. And they're kind of having to manually puzzle out, oh, if I want the network to look a certain way where, oh, this one is way too dense and this isn't like my real network. So I have to go in and I have to turn the edges parameter down and then see if that like kind of produces what's the network pattern that I want. So they're kind of like manually going through that process of what the ergom does automatically. And hopefully that helps them kind of build intuition about what's going on under the hood.
Usually that we use for the interface model. So here that we use this for demonstrate the ERG. And what's the difference? What's the difference between the basic control and especially in the case that we design works. Then also that some of my team members that they used to use analog doing the ABM. And for us, that I think the most difficult part is that's the parameter setting. And so also that I think that using the analog will require kind of programming technique. So for the students that who are not really familiar with the programming, would not be possible to use the set of more
So first question is about the difference between ABM and ergom, and second question is about is there any like entry boundary like for using this specific tool?
Yeah, especially does it require the programming skills?
Yeah, those are two very good questions. So like we built this tool in NetLogo just to kind of utilize the NetLogo web capabilities of like easily running in your browser. But this exercise doesn't necessarily have to do, or you don't have to really teach them anything about agent-based modeling. It's kind of just an implementation of like kind of the ergom algorithm. So what it does when I hit go is kind of just doing a Markov chain Monte Carlo process for updating the ties. And it's sort of the same thing that is kind of happening with Markov chain Monte Carlo if you're running ergom in like R or another environment. So it was just kind of a convenient place to program it was in NetLogo, but it's not really different than an algorithm you could write in any sort of coding language or coding environment. So we don't always, we sometimes run this before we've taught the students about agent-based modeling at all, or we're not covering that as a focus in the class. And that's generally fine with like, we just kind of introduce them to the interface with, I think, a little bit more of an elaborate explanation than I've given today. And also on the kind of handout, we cover that the first page is kind of describing the exercise. The second page has a lot more detail on like the different commands in there. And for the activities, we kind of walk you through like very specifically, these are the things you should set up as fixed. This is what they mean. And here are the like 2 things you should be experimenting with at a time to try to make it like more manageable so that this could be taught to students without teaching them, like, they don't have to have any knowledge of NetLogo at all. They don't need to ever code in it. And they don't really need an understanding of agent-based modeling. Of course, we've also like sometimes taught this like after we've already covered or introduced the idea of agent-based modeling. And then that's a little different where we could, if we want to, like talk a bit more about how this is related. But this exercise doesn't really have to be tied to agent-based modeling at all, other than the fact that we happen to be using like a programming language that's also used for AVMs.
In addition to that, if you are interested in teaching the stochastic actor-oriented models, that's directly based on the agent-based modeling idea. So often, like we teach the arguments first, and then showing this exercise. Then they have some intuition of agent-based modeling. Then introducing the stochastic actor-oriented models. Then students have a much better understanding of what that model works, because that model is actually simulating using agent-based modeling idea.
But for this tool, and then also on operating this platform, if the student have been then they can then this platform only show the multi-model simulation.
Exactly. Yeah, the students don't need to program or anything.
Just treat the parameters.
One cool use case of this is just playing around with it is that you could show, or you can get structural effects. So there's this distinction between outcome and process. So, for example, homophily could be generated by other processes like
Exactly. Yeah.
try to closure.
Mhm.
This is really cool too.
Yeah, exactly. So I think we already introduced like all the activities we have, and so any like final comments like to all the activities or any recommendation? Yeah.
Just had a quick question for the network signatures, because there's some, I looked up the Harvard Business article. Do you guys have a guide with like the actual formulas for some of the signatures? Because it's described qualitatively.
Yeah, so we have that in the current version of the report. If once those are like sent out, it will be kind of in an appendix at the end of the report where there's like more technical details. So that's definitely something I would maybe emphasize more if I was like embedding like the personal network report and like in like a semester long class where I'd like, if I'd already like covered the idea of like Bert's constraint, that's something I can like directly reference the connection. Whereas if I'm just doing the personal network report in like a one-off workshop at a company or with like MBA students, I might not go into the details about the signatures. But the information that's more technical should be in the appendix of the report.
I think what that suggests, your question suggests is that in addition to having it in the report, if we have an instructor's note, that this, all the formulas should be included in the instructor's note so that you as an instructor can see it even before the students do and understand what the formulas are. But all the formulas are in there. So I think it'd be a good idea to just put it into an instructor's note or a teacher's note as the case.
I think we can put it like in the participant handout, like Google Docs, so people all have.
All of you can see,
Yeah.
yeah,